All right, welcome to The Explainer. Today, we're going to pull back the curtain on the technology that creates those breathtakingly realistic images you see in movies and video games. We're talking about ray tracing.
So, you ever wonder how they do that? How do they make a completely digital world feel so real? The answer is a process called rendering, and the absolute gold standard for it is an algorithm called path tracing. It's the most advanced version of ray tracing, and it's basically the secret sauce behind all of it.
And to really get your head around the complexity here, just imagine this. If the entire population of the planet, every single person, did one calculation per second, it would still take all of us 12 straight days to render just one complex frame of a movie. Yeah, the number of calculations is just mind-boggling.
So how in the world did we go from that impossible task to something we can do on our computers at home? Well, let's dive in and find out. We're going to look at the impossible image, tracing light backwards, painting with shadows, cracking the code, and finally, realism in real time.
Okay, so before we can really get into the clever solution, we have to appreciate just how massive the problem is. When a CGI artist builds a scene, they aren't just drawing a picture. No, they're literally constructing a virtual universe from the ground up. It's a whole pipeline. First, they build everything you see, the spaceships, the characters, the buildings, out of millions and millions of simple triangles. Then they paint them with textures and materials to say, hey, this is shiny metal and this is rough stone. They set up lights, they place a virtual camera, and then they hit the render button and hope for the best.
And that render button is where we run into a brick wall. See, in the real world, a light source like the sun is shooting out a practically infinite number of light rays in every single direction. Trying to simulate all of them is not just computationally impossible, it's also super wasteful, because most of those rays will fly off into space and never even reach our camera.
So here it is, the big aha moment. Instead of simulating trillions of rays from a light source and just hoping a few of them find their way to the camera, the pioneers of this tech had a brilliant idea. What if we worked backwards? And that is the core genius of path tracing. It completely flips the problem on its head. By shooting rays out from the camera, we guarantee that every single calculation we do actually matters. It's all about only simulating the light paths that are going to end up in the final picture. No wasted effort. So here's how that works. A 4K image, for example, has 8.3 million pixels. So for every single one of those pixels, the computer shoots out a primary ray from the camera, straight through that pixel, and into the scene. Whatever that ray hits first, that's what determines the basic color for that pixel.
Okay, but that's just step one, right? Just knowing an object's color gives you a pretty flat, kind of cartoonish looking image. The real magic, the realism, comes from how that object is lit. We're talking highlights, shadows, reflections. It's why the water in your favorite game can look so incredibly real.
See, realistic lighting is really a mix of two things. You've got direct illumination, which is pretty simple. That's light coming in a straight line from a lamp or a light bulb. But then you have indirect illumination, and that's all the light that's been bouncing around the room off of other things before it finally hits our object.
So to figure all this out, the moment our primary ray hits something, the computer sends out new rays from that exact spot. Shadow rays shoot out towards the lights to check, hey, is anything blocking the way? And then secondary rays bounce off in random directions to see how everything else in the scene might be lighting up that single point. And here's where it gets really, really cool. That bounced light, it actually carries color information with it. So if a secondary ray bounces off a bright red wall, it picks up a bit of that red and carries it to the next thing it hits. This is called color bleeding, and it's one of those subtle effects that just makes a digital scene feel totally cohesive and real.
All right, so we've got this beautiful, elegant process, but it's still, unbelievably complex. We still have two giant roadblocks to deal with. First, the sheer number of rays we have to trace. And second, for every single ray, figuring out which one of the millions of triangles in the scene it's going to hit.
I mean, just look at this. A really complex scene can have over 8 million triangles. Can you imagine trying to check every ray against every single one of those triangles? Your computer would just give up. It would take forever.
So the first big breakthrough was this incredibly clever software trick called a bounding volume hierarchy, or BVH. The best way to think about it is like a process of elimination. It groups all the triangles into bigger and bigger nested boxes, so the computer can just check if a ray hits a big box. If it doesn't, it can instantly ignore the thousands of triangles inside it. It's a shortcut that turns millions of checks into just a handful.
The second piece of the puzzle was pure hardware muscle. Modern graphics cards now have these specialized little circuits on them called ray tracing cores, or RT cores. These things are tiny engines built to do one thing and one thing only: calculate ray intersections at lightning speed. It's not software, it's literally built into the silicon. It's pure, purpose-built speed.
And this slide just says it all. The progress is absolutely staggering. Back in 2000, the world's fastest supercomputer cost $110 million and could do 12.3 trillion operations a second. By 2022, a graphics card you can buy for a couple $1,000 could do 36 trillion. That is supercomputer power right inside your home PC.
Okay, so that's how movies do it. But what about video games? This is where things get really intense. A movie has months to render, but a game needs to spit out a new frame every 16 milliseconds. It just can't afford to wait.
So games use some really smart cheats. One popular method is creating light maps, where all that complex bounce lighting is calculated beforehand and just kind of baked into the scene's textures. Another is screen space ray tracing, which fakes those incredible reflections in puddles by only using information that's already visible on your screen. But there's a catch with that screen space trick. Because it can only see what's on the screen, if an object moves out of your view, its reflection just vanishes instantly. It's a clever hack for sure. You get about 90% of the visual wow for a tiny fraction of the cost, and that's a trade-off you have to make to get a smooth 60 frames per second.
So when you boil it all down, what you should really take away from this is how this incredible technology, an idea that was just a dream back in 1986, needed decades of innovation in both software algorithms like BVH and hardware like RT cores to finally become the reality we get to play with today.
And that just makes you wonder, right? As our computers keep getting ridiculously powerful, what are the visual effects that seem impossible to us today that will just be standard for the movies and games of tomorrow? What's the next big leap going to be?